Hey guys, welcome to the very last lesson in your stats book. This is 12.4. So we're going to start out just kind of talking about something to get some ideas going about the direction this lesson is heading. So let's say that we want to predict what someone's height is going to be, okay? So we want to think about the variables that might affect the person's height. Clearly, one of those would be age, okay? Definitely, older people are taller when you're talking about kids. Other things might be the height of parents. Okay, people who have taller parents tend to be taller people in general. Race can be a factor when you think about often Asian people tend to be a little bit shorter than maybe some other races, so that definitely is a factor. Let's see, what else could it be? Oh, nutrition, right? If someone who does not have adequate nutrition is not going to grow adequately. So those are just a few of the things that might affect a person's height. Now, we want to think about which one affects height the most. Well, if we're talking about kids, I would definitely pick age. Okay, so if you're talking about from 0 to 18, that's going to be the biggest predictor is how old you are, the biggest predictor of your height. If we're talking about adults, it might be something more like the height of your parents, maybe it. Now, what we did last several sections is we wrote regression equations. Okay, so we wanted to predict someone's height, y hat, based on their age, and we would make this our x value. Okay, and then we would have some sort of equation with a y-intercept and a slope, and it would predict it. But what if we want to create an equation that takes all of these things into consideration? Not just age, not just height of parents, but race, nutrition, maybe some other factors that we didn't think about. So what we want is, instead of just this plain old linear model, is we want to think about age as a variable. So maybe we call that x1. We want to think about height of parents as a variable, or maybe we even break that up between height of mom and dad as a variable. We want to think of race as a variable. So we can turn our equation into something that has multiple variables like this. And we'll need all of these coefficients. That is exactly what we're doing in 12.4. So the last section, we created a regression line that modeled the relationship between two variables, and these are what our equations look like. Remember, this is for the population is y. We don't ever know beta 0 and beta 1 because we would need a census. So we used our statistics to get an equation for y hat, and these are statistics, so they're estimates. Now, we can expand that idea into a multiple regression model. So it's still a linear regression using two or more explanatory variables. Okay, so it's still the y hat, and you'll see you have your intercept, and then b1, x1, whatever your first variable is, b2, x2, whatever your second, and you can have as many as you want. We cannot do these by hand, and your calculator doesn't do these either. They have to be done on Google Sheets. So before we get to Google Sheets, I want to show you how to interpret the tables that Google Sheets are going to spit out at you. Okay, so they're called ANOVA tables, and this is what they look like. So the first thing, sample problem that we want to look at is children's reading levels, and we looked at reading levels based on age in the last lesson. So we definitely know that the older a child gets, their reading level generally goes up, and those are the two columns we were looking at before. But there could be other factors in there. Maybe their teacher that they have, a more experienced teacher is maybe a better teacher, and so they're maybe making more gains. Parents' education, so however many years of school the parents completed, that may determine a child's reading level because maybe there's more books in the home or they're exposed to more vocabulary and that kind of thing. So we've got data on that. For parents' education, so like a 10.2 means you went 10th grade and a little bit more, 11th grade a little bit more. So a 12 would be a high school graduate, so anything above 12 would be a little bit of college. A 16 would be a college graduate. I don't think we have anything much beyond that. Okay, so that's how education works out. I'll show you how to get these tables in Google Sheets eventually, but when you get Google Sheets to spit out an ANOVA table, this is what it looks like, okay? Lots of numbers, lots of things that we need to pull apart. So the first thing that we'll see is our multiple R and R squared, and adjusted R squared and standard area, okay? Multiple R is just your correlation coefficient R, and a multiple coefficient of determination is just R squared, okay? Now, the more variables you have, just by nature, your R values are going to get closer and closer to 1. So we have this thing called adjusted coefficient of determination that kind of mitigates that effect, okay? It adjusts for having so many variables. But you can see for whatever data we are dealing with here, it is very good. Oh, this is the children's reading data, I believe. You know, our R squared value is 0.99, so this is a very strong correlation. We can see if it's statistically significant. This is more of our ANOVA testing. And we've got lots of sum squared errors and all of these things we don't really need. The only thing we need is over here under significance F, that's our p-value. Okay, so we're going to compare this to alpha. Clearly this one is less than alpha, so this is statistically significant. And then you have this with your coefficients, which we definitely want. And then there's some more information on those, which we'll get to. Okay. So to determine if this is a good fit, we conduct a hypothesis test. Remember, our ANOVA hypothesis test is we are comparing multiple things. So our hypothesis test is always the same for these ANOVA tests, is that beta 1 equals beta 2 all the way up to beta k is 0. Okay, so the null hypothesis is saying there's no relationship here, there's no linear relationship, all the coefficients are 0. And then the alternative is at least one coefficient is not equal to 0. So if we reject the null hypothesis, this means, put this here where I can actually type. So this means there is evidence to support that there is a significant relationship between at least one of the typing is really hard today, as you can see. Okay, let's clean that up and make it so we can actually read it. All right, so if we decide to reject the null hypothesis, that means there's evidence to support there's a significant relationship between at least one of the explanatory variables and the response variable. Okay? If we fail to reject, this means that all of the explanatory variable coefficients are 0, so there is not a significant linear relationship. I've got smaller so you can actually see everything here. Okay. All right, so our null hypothesis is, remember that all the coefficients are 0, so there's no linear relationship, and then our alternative is that at least one of the coefficients is not 0, so that there is a significant relationship between at least one of them. We don't know how many, we don't know which one yet. We'll dig into that in just a minute. So going back up to this example, that's what this p-value is telling us. That is small enough that we would reject the null and we would say, oh, at least one of the coefficients is not 0. There is some sort of significant relationship between one of these explanatory variables and reading level. Okay, it might be age, teacher experience, parent education. It might be more than one, but we know that at least one of them is significant. Okay, we will flip over to the next page and just keep talking about this. All right, so the coefficients are our predicted values, And then remember, like we talked about last lesson, there is a confidence interval, and that can be found with your lower and upper 95%. The ANOVA table gives you 2 of these. Generally, there is very little difference between the 2. I'm not sure why the ANOVA table spits out 2 of them. I think maybe you can set one of them to be 95% and the other one 99%. We're not going to bother with that. So these columns should be pretty much the same. Okay. So we want to use the output of the table to write a regression model for predicting the child's reading level based on the child's age, teacher's experience, and the parent's education level. All right, so to do that, I'm going to move these. I'm going to put the answer up here so that way we can actually see the table as we type this. All right, so our equation is going to be y hat. And now we need to start looking at our coefficient. This first one here, it says intercept. So that's our first, negative 6.98. Plus, and then we'll go to our next one, is age. So we'll do 0.898 x1. When you write that, you want that to be a subscript. I don't have subscripts right now. Plus, and then we have the next one. Oh, actually, that's a minus. Minus 0.003. No, just one O. 33 x2. And then the next one is positive, so plus 0.232 x3. And like I said, these are subscripts, so I'll just make them smaller. There. Okay. Now, the other thing that you need to make sure you do with this is you need to say what x1, x2, and x3 are. This answer right here is not good enough. Okay, so what we'll do is we'll say where x1 was age, x2 is teacher experience, and x3 is parent education. Okay, so you have to include that. We need to explain what x1, x2, and x3 are. Okay, but that would be the answer. Here, we'll copy this and put it down where it actually belongs. There. Yeah. Okay. All right. The next one, we want to use the regression model to predict the reading level of a child who is 10 years old, with a teacher who has 8 years of experience, and parents with an average of 17.2 years of education. So let me switch over to a pencil for this. So we want to predict, so we want to find this y hat. So we're just going to plug into the equation. We're going to plug in exactly what we have. So our y-intercept is negative 6.98 plus 0.898. x1, remember x1 is age, so that we are talking about a 10-year-old, minus 0.033 x2. x2 is teacher experience, which is 8 years, plus 0.232 x3, which is parent education, which is 17.2. So we're just plugging all that in and stick it in the calculator and see what we get. And I wrote this down somewhere. I got 5.7. Okay, so we would expect a child in this circumstance to have an 10-year-old with a teacher with 8 years experience, parents who have an education of 17.2, that this child's reading level is a 5.7. Now remember, that's just an estimate, may not be exact, but it gives us a good idea. All right, now there is one other thing I want to point out in that ANOVA table, and it is the p. There's a column of p-values in the output. A small p-value indicates there's sufficient evidence to support that coefficient is not 0. So that means the linear relationship between this particular variable and the response variable is statistically significant. What that p-value does is if we have a p-value that's large, that means that particular variable may not be affecting the reading level that much. So we're going to take a look at this and find out, according to the output, which explanatory variable may not be useful in predicting a child's reading level. So let's go back to this. This is the column that we're looking at. Okay. So each one of our coefficients here, so we're talking about these coefficients, each one of those has an associated p-value. Okay. So like age, that's a very small p-value, which means that is statistically significant. Age does seem to be a strong indicator of reading level. Notice parent education, 0.02, that's less than alpha. So parent education also has a statistically significant relationship. This one, 0.535, that is greater than alpha. Okay, so what's this saying? What this is saying is this particular piece may not be useful. So teacher experience may not really be useful in predicting a student's reading level. Okay, so that's what we would say for this one, wherever it is. Okay, we would say teacher experience may not be useful since the p-value that we had was 0.535. Okay. Now, this does not mean that we should throw that out of our equation, because that would cause us to have to write a new equation. So you don't want to take this piece out of the equation. Just know that it's really not doing much in terms of predicting what the child's reading level is actually going to be. Okay. Now, in the last video, there's a Google Sheet that you're going to use. I've attached it along with the notes, and there's actually two different sheets on it, and we're going to determine if there's a statistically significant relationship between the explanatory and the response variables there, and write the equation. Okay, so I want to show you how to actually get Google Sheets to do this ANOVA table for you. So that will be in the next video.